According to the National Electrical Code Article 215, the size of the feeder conductors for a motor control panel should be based on the sum of the nameplate currents of all motors connected to the panel. A commonly used rule of thumb is to select feeder conductors that are one size larger than the largest sub-breaker in the panel. However, this method does not guarantee compliance with NEC regulations. In this case, the largest sub-breaker is 20 amps. Using the National Electrical Code rule, the sum of sub-breaker currents is 2 times 20 amps plus 15 amps plus 10 amps plus 3 times 5 amps, which equals 80 amps. Therefore, the feeder conductor should be at least number 8 American wire gauge for copper to handle the load current of 80 amps. Also consider the voltage drop along the feeder conductors to ensure that the motors receive adequate voltage. Allow for additional capacity in the feeder conductors if there is a possibility of future expansion or modifications to the panel. Check manufacturer's specifications for the maximum allowable current for the feeder conductors. Always recommended to consult with a qualified electrician or engineer to ensure compliance with local codes and regulations. When sizing conductors for an industrial control panel, several factors must be taken into account to ensure safety, compliance with regulations, and optimal performance. Firstly, the National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations, including control panels. Secondly, understanding the relevant articles and sections of the NEC is crucial for determining the appropriate conductor size. Thirdly, NEC Article 215 specifically addresses feeder conductors for motor control panels. One must calculate the total load current that the feeder conductors will carry. This involves summing the currents of all the sub-breakers and motor loads connected to the panel. The NEC provides methods for calculating motor full load currents based on horsepower and voltage ratings. After determining the total load current, the next step is to select a conductor size that can safely handle this current. The NEC provides tables, such as Table 310.16, that list the ampacity of various conductor sizes based on their insulation type and temperature rating. It is essential to choose a conductor with an ampacity greater than or equal to the calculated load current. However, ampacity is not the only factor to consider. Voltage drop can be a significant issue, especially in long conductor runs. Excessive voltage drop can cause motors to operate inefficiently or even fail to start. The NEC recommends limiting voltage drop to a maximum of 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to know the conductor length, current, and resistance. There are online voltage drop calculators available that can simplify this process. If the calculated voltage drop exceeds the recommended limits, you may need to increase the conductor size. In addition to load current and voltage drop, you should also consider any directing factors that may apply. Directing factors are adjustments to the conductor ampacity to account for conditions such as high ambient temperatures or multiple conductors bundled together. The NEC provides tables and guidelines for applying directing factors. For example, if the ambient temperature is above 30 degrees Celsius, the conductor ampacity must be derated according to Table 310.15b2. Similarly, if more than 3 current-carrying conductors are bundled together in a conduit, the ampacity must be derated according to Table 310.15b3. Another important consideration is the type of insulation used for the conductors. Different insulation types have different temperature ratings, which affect their ampacity. Common insulation types include THHN, THWN, and XHHW. THHN and THWN are suitable for dry and damp locations, while XHHW is suitable for wet locations. It is essential to choose an insulation type that is appropriate for the environment in which the conductors will be installed. The conductor material also affects its ampacity. Copper conductors have a higher ampacity than aluminum conductors for the same size. Copper is generally preferred for control panel wiring due to its higher conductivity and corrosion resistance. However, aluminum conductors may be used in some applications, especially for larger feeder sizes. When using aluminum conductors, it is essential to use connectors that are specifically rated for aluminum and to apply an antioxidant compound to the connections to prevent corrosion. The type of overcurrent protection used in the control panel also affects the conductor sizing. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the conductors from overloads and short circuits. The NEC requires that the conductor ampacity be at least equal to the rating of the overcurrent protection device. For example, if the feeder conductors are protected by a 60 amp circuit breaker, the conductors must have an ampacity of at least 60 amps. The NEC also provides specific rules for sizing conductors for motor circuits. These rules are more complex than the general conductor sizing rules and take into account the motor's starting current and duty cycle. The motor full load current is multiplied by a factor, typically 1.25, to account for the starting current. The resulting value is then used to determine the minimum conductor ampacity. In addition to the NEC, other standards and regulations may also apply to control panel wiring. For example, the National Fire Protection Association, or NFPA, publishes standards for industrial machinery, such as NFPA 79. These standards may provide additional requirements for conductor sizing and wiring practices. It is essential to be familiar with all applicable standards and regulations to ensure that the control panel wiring is safe and compliant. A practical example: consider a control panel with a 60 amp main breaker and the following sub-breakers: two 20 amp 3-pole breakers, one 15 amp 3-pole breaker, one 10 amp 3-pole breaker, and three 5 amp 1-pole breakers. To determine the appropriate size for the feeder conductors, start by calculating the total load current. The sum of the sub-breaker currents is 2 times 20 amps plus 15 amps plus 10 amps plus 3 times 5 amps, which equals 80 amps. Based on this calculation, the feeder conductors should have an ampacity of at least 80 amps. According to Table 310.16 in the NEC, number 8 American wire gauge copper conductors with THHN insulation have an ampacity of 55 amps at 75 degrees Celsius. However, since the calculated load current is 80 amps, number 8 American wire gauge conductors would not be sufficient. The next largest size, number 6 American wire gauge copper conductors with THHN insulation, has an ampacity of 65 amps at 75 degrees Celsius. However, this is also insufficient as it is less than the required 80 amps. The next largest size, number 4 American wire gauge copper conductors with THHN insulation, has an ampacity of 70 amps at 75 degrees Celsius. This is still insufficient. The next largest size, number 3 American wire gauge copper conductors with THHN insulation, has an ampacity of 75 amps at 75 degrees Celsius. This is still insufficient. The next largest size, number 2 American wire gauge copper conductors with THHN insulation, has an ampacity of 95 amps at 75 degrees Celsius. Since the feeder conductors are protected by a 60 amp main breaker, conductors with an ampacity of at least 60 amps are required. Therefore, number 2 American wire gauge copper conductors with THHN insulation would be acceptable for this application. However, you should also consider voltage drop and derating factors to ensure that the conductors are adequately sized. If the conductor run is long or the ambient temperature is high, you may need to increase the conductor size further. Another approach, the rule of thumb, suggests selecting feeder conductors that are one size larger than the largest sub-breaker in the panel. In this case, the largest sub-breaker is 20 amps. Therefore, the feeder conductors should be at least number 12 American wire gauge copper conductors with THHN insulation, which have an ampacity of 20 amps. However, this rule of thumb does not always guarantee compliance with the NEC regulations. In this case, the calculated load current is 80 amps, which is much higher than the ampacity of number 12 American wire gauge conductors. Therefore, it is always best to perform a detailed calculation based on the NEC requirements. In summary, sizing conductors for an industrial control panel requires a thorough understanding of the NEC regulations, load calculations, voltage drop considerations, derating factors, and conductor properties. Following these guidelines ensures a safe and reliable electrical installation. Remember that it is always recommended to consult with a qualified electrician or engineer to ensure compliance with local codes and regulations. A deeper dive into the NEC reveals further nuances and requirements. Firstly, Article 310 provides general requirements for conductors, including ampacity ratings, insulation types, and installation methods. Secondly, Article 430 covers motors, motor circuits, and motor controllers, including specific rules for sizing conductors for motor applications. Thirdly, Article 500 addresses hazardous locations, which may require special types of conductors and wiring methods. The NEC also provides guidelines for grounding and bonding of control panels. Grounding is the process of connecting electrical equipment to the earth to provide a low impedance path for fault currents. Bonding is the process of connecting different metal parts of the electrical system together to create an electrically conductive path. Proper grounding and bonding are essential for preventing electrical shock and ensuring the safe operation of the control panel. The NEC requires that all metal enclosures and equipment in a control panel be grounded and bonded. The grounding conductor must be sized according to the NEC Table 250.122, which is based on the rating of the overcurrent protection device. The bonding conductors must be sized according to NEC Table 250.102, which is based on the size of the largest ungrounded conductor. In addition to the NEC requirements, there may also be local codes and regulations that apply to control panel wiring. It is essential to check with the local authorities to ensure that the control panel wiring is compliant with all applicable codes and regulations. Proper documentation is also crucial for control panel wiring. The control panel should have a wiring diagram that shows all of the conductors, components, and connections. The wiring diagram should be accurate and up to date. The control panel should also have a nameplate that lists the voltage, current, and other important information. The nameplate should be permanently affixed to the control panel and should be legible. Regular inspection and maintenance are essential for ensuring the continued safe operation of the control panel. The control panel should be inspected periodically to check for loose connections, damaged conductors, and other potential problems. Any problems should be corrected promptly by a qualified electrician. The control panel should also be cleaned regularly to remove dust and dirt, which can cause overheating and other problems. The frequency of inspection and maintenance should be determined based on the operating environment and the type of equipment in the control panel. In addition to the technical aspects of conductor sizing, it is also important to consider the practical aspects of control panel wiring. Firstly, the conductors should be neatly and securely installed. Secondly, the conductors should be properly labeled to identify their function. Thirdly, the conductors should be protected from physical damage. The conductors should be routed in a way that minimizes the risk of abrasion, cutting, or other damage. The conductors should be supported by clamps, ties, or other means to prevent them from sagging or rubbing against sharp edges. The conductors should be protected from moisture, chemicals, and other corrosive substances. The conductors should be protected from excessive heat. The conductors should be installed in a way that allows for easy access for maintenance and repairs. The conductors should be installed in a way that minimizes the risk of electrical interference. The conductors should be separated from other conductors that may carry high-frequency signals. The conductors should be shielded to prevent electromagnetic interference. The conductors should be grounded to reduce noise. In conclusion, sizing conductors for an industrial control panel is a complex process that requires careful consideration of various factors, including the NEC regulations, load calculations, voltage drop considerations, dirting factors, conductor properties, grounding and bonding requirements, local codes and regulations, documentation, inspection and maintenance, and practical aspects of control panel wiring. By following these guidelines, you can ensure a safe, reliable, and compliant electrical installation. Always consult with a qualified electrician or engineer for complex or critical applications. They possess the expertise to navigate the intricacies of electrical codes and ensure the safety and efficiency of your control panel. Remember that electrical work can be dangerous, and it's always best to err on the side of caution. Consider the long-term implications of your conductor sizing decisions. Over time, the demands on your control panel may change. It's often wise to build in some extra capacity to accommodate future expansion or modifications. This can save you time and money in the long run by avoiding the need to rewire the panel later. Stay informed about changes to the NEC and other relevant standards. Electrical codes are updated periodically to reflect new technologies and best practices. Keeping your knowledge current will help you ensure that your control panels meet the latest requirements. Invest in quality tools and materials. Using the right tools and materials can make the wiring process easier, faster, and safer. Choose conductors, connectors, and other components that are specifically designed for control panel applications. Proper training is essential for anyone working on electrical control panels. Make sure you have the necessary skills and knowledge to perform the work safely and correctly. Consider taking courses or workshops on control panel wiring and NEC compliance. The color coding of wires within a control panel is another important aspect to consider for safety and ease of maintenance. While the NEC doesn't mandate specific color codes for all applications, it's a common practice to follow industry standards. For example, black is often used for line voltage, white for neutral, and green for ground. Consistent color coding can help prevent wiring errors and make it easier to troubleshoot problems. Labeling wires and components is also crucial for maintainability. Clear and durable labels make it easy to identify the function of each wire and component. This can save time and reduce the risk of errors during maintenance and repairs. Use a labeling system that is consistent and easy to understand. Consider the environmental conditions in which the control panel will be operating. If the panel will be exposed to moisture, chemicals, or extreme temperatures, you'll need to choose conductors and components that are specifically designed for those conditions. Using the wrong materials can lead to premature failure and safety hazards. Pay attention to detail when making connections. Loose or poorly made connections can cause overheating, voltage drops, and other problems. Use the correct crimping tools and techniques to ensure that connections are tight and secure. Inspect all connections carefully before energizing the control panel. Document all changes and modifications to the control panel. Keep a record of any changes that are made to the wiring, components, or configuration of the panel. This documentation can be invaluable for troubleshooting problems and making future modifications. Store the documentation in a safe and accessible location. Develop a checklist for control panel wiring inspections. A checklist can help ensure that you don't overlook any important steps during the wiring process. The checklist should include items such as conductor sizing, voltage drop calculations, grounding and bonding, overcurrent protection, and labeling. Use the checklist consistently to ensure that all control panels are wired to the same high standards. By paying attention to these additional considerations, you can further enhance the safety, reliability, and maintainability of your industrial control panels. Remember that continuous learning and improvement are essential for staying ahead in the field of electrical control panel wiring.